Alright, welcome back to CECS 228. Today we're going to finish the Relations Part 2 set of lecture notes. We left off with representing relations using digraphs. So the first type of representation that we saw for relations was using matrices. And we saw how we could use a matrix representation to determine whether a relation is reflexive, symmetric, antisymmetric, transitive, and all of those properties. Now we're going to take a look at how we can use a directed graph, also known as a digraph, to read off those same properties. So let's start with the definition. A directed graph or digraph consists of a set V of vertices or nodes together with a set E of ordered pairs of elements of V called edges. So basically it is a set of vertices along with a set of edges. A vertex A is called the initial vertex of the edge A, B, and vertex B is called the terminal vertex of this edge. So edges are represented as ordered pairs. The first coordinate or the first entry of the ordered pair is going to be the initial vertex or the node from which the edge emanates, and B is the terminal vertex, meaning it is the vertex that receives or is the end of the edge. An edge of the form A, A is represented using an arc from the vertex back to itself, and that is also called a loop. The directed graph of vertices A, B, C, and D and edges A, B, AD, BB, BD, CA, CB, and DB is in this figure. So if we look at, for instance, the edge AB, that is represented with an arrow or a pointed edge from A to B. Then A, D would be an edge emanating from A going towards D. Then B, B, that is represented by a loop. B, D is an edge going from B to D. C, A is an edge from C to A. C to B, same idea. And D to B is this backwards going edge. And so we're going to use those ideas or this definition to draw the directed graph of the relation that contains these elements over the domain 1, 2, 3, and 4. So I'll go ahead and represent, or I'll order those in a type of box. So this will be vertex representing element 1, vertex representing 2, 3, and 4. And then we have 1 going to 1, so that is a loop. Okay, going back to itself. Then we have an edge from 1 to 3. We have an edge from 2 to 1. We have an edge from 2 to 3. We have an edge from 2 to 4. An edge from 3 to 1. An edge from 3 to 2. And an edge from 4 to 1. And so that would be the digraph for that relation. Right, now let's go in the backwards direction. What ordered pairs in the relation R are represented by the digraph in figure 5? So we can start with looking at the ordered pairs that have 1 as the initial vertex. So 1 maps to 4 and to 3. So 1 to 3 and 1 to 4. Okay. From there, we've taken care of all of the edges that are emanating from 1. If we take a look at 2, there are 3 edges that emanate from 2. There is 2 to 1, 2 to itself, so that'd be a 2 to 2. We also have a 2 to 3. Okay. Next, we'll take a look at vertex 3. Vertex 3 has 2 edges emanating from it. 1 going to 1, so 3 to 1, and then another go into itself, so that's 3 to 3. Okay, and then last vertex would be 4. 4 has 2 edges emanating from it, so one going to 1 and the other going to 3. And just to make sure, the number of ordered pairs should be consistent with the number of edges. If we count the number of edges, we have 4, 5, 6, 7, 8, and 9. So here we also have 9 ordered pairs. That means that we have those, or it's a good indication that perhaps we have it correctly. Okay, let's take a look at these properties of reflexivity, symmetry, and anti-symmetry. If we have the digraph of relation R, we can tell whether a relation is reflexive, and recall reflexive means that for every element in the domain, there is an ordered pair that is the element with itself. And so basically, if we have for any element A, I'm going to call the domain A. Okay. We have that A comma A as part of the relation. That's what it means to be reflexive. And so on the graph, what that's going to look like is for every node or for every vertex on the graph, there's going to be a loop that is part of the node, meaning everything is going to map back to itself. So a relation is reflexive if all nodes, all vertices, have a loop. And what about symmetric? Well, symmetric meant that for any two elements in the domain, if A comma B was part of the relation, then that meant that B comma A would also be part of the relation. Oh, and I wrote it at the wrong place. Let's write that up here. Okay. So, what would that look like then on the digraph? Well, that means that whenever there are two vertices that are connected by an edge, there needs to actually be a double link, meaning there has to be two edges, one going, let's say from A to B and then from B to A. So a relation is symmetric if every pair of nodes that is connected is doubly linked. So, i.e., there are two edges connecting the two nodes. Okay. And then the next part, a relation is antisymmetric. Remember, antisymmetric meant that if AB is part of the relation, then B comma A cannot be part of the relation unless B is equal to A. So, or A is equal to B. Okay, so what does that mean in terms of the digraph? In terms of the digraph, that means that for every pair of node that is connected, it has to be singly linked. Now, the other thing that we have to make note of, because this is going to differentiate antisymmetric from asymmetric, is that loops are allowed, right? So if AB is an R, that means that BA cannot be an R, or if it is, then that means that A is equal to B. That means that you can have A comma A as part of the relation. So that A comma A corresponds to a loop. That means that loops are allowed. Okay, in a relation that is asymmetric, you're going to be looking for nodes, you're going to be making sure that all edges have only one edge, or all pair of nodes that are connected have only one edge connecting them. But you're also going to make sure that loops are not present for asymmetric. For antisymmetric, loops are allowed. Okay, so let's use that for example number 10. For example number 10, they're asking us to determine whether the relations R and S in this figure are reflexive, symmetric, and antisymmetric. Okay, and it's a little difficult to see on my notes here because it didn't print too well, but this is the digraph of relation R, and this is the digraph of relation S. Okay, so let's start with relation R. We're going to start by looking at whether or not it's reflexive, and if it's reflexive, that means that we need to have loops at all of the nodes, and we do see loops at all of the nodes, so it is reflexive. Okay. Next thing, is it symmetric? Well, let's see. Symmetric requires that for any for any pair of distinct nodes, there are two edges that connect them. Here, there is only one pair of nodes that are doubly connected or doubly linked. All the other ones have a single link. So there is an element A to B, but there is no element B to A. So it's not symmetric. Alright, is it antisymmetric? Okay, for antisymmetric, we said for any pair of distinct nodes, we require that there is only one edge connecting them. And as you can see here, there are two edges connecting B and C, meaning there is the element B comma C in R, but also C comma B. So the answer here is no. Okay, so that is relation R. Let's take a look at relation S. Is it reflexive? Well, we would require loops at all of the nodes, and here both A and C are missing loops, so that means that it is not reflexive. Okay, we could write there are not all of the nodes have loops, but we could also just simply write A comma A is not part of the relation, and that already violates the reflexivity. Is it symmetric? Well, symmetric again requires, excuse me, that we have two edges between every pair of connected nodes. And in this case, we do see that being the case, right? For between A and B, there are two edges. Between A and D, there are two edges. And between A and C, there are two edges. So we'll say yes. Every pair of connected nodes is doubly connected. Alright, the next property is it anti-symmetric? Well, this is going to be definitely a no. If it's symmetric, it can't be both anti-symmetric and symmetric. The answer here is no. And again, you can say as a justification the nodes that are connected are doubly linked, or simply in this case, I'm going to write no because it's symmetric. We now begin relations part 3, which deals with the equivalence relations and partial orderings. And so as an introduction, we want to consider maybe the C language and see how Despite not, dealing with functions, relations can still offer us a great deal of structure and can be used to describe, different situations in computer science. So in the C language, the variable names can have any given length. However, the compiler is only going to check the first 8 characters of the string. Hence, if two variable names begin with the same first 8 characters, they will be considered to be the same. So we can define a relation R on the set of all strings such that S and T will be an ordered pair in the relation if string S and string T agree in their first 8 characters, meaning the C language or the C compiler is going to consider both of those strings to be the same. In such case, we see that R is going to be reflexive, meaning every string will have the same first 8 characters as the string that is also itself that reads the same name. So it'll be reflexive. It's going to be symmetric because if S and T both share the same first 8 characters, then T and S, the same can be said about T and S, so it'll be symmetric. And finally, it's transitive because if S and T share the first 8 characters and T and R, let's say, share the first same 8 characters, then S and R also have to share the same first 8 characters. Okay, so what we've just described then, this relation that is reflexive, symmetric, and transitive, is called an equivalence relation. And in such a case, we say that S and T are equivalent under the relation R. Okay. And that's in general what the definition is, or that is what the definition is in general for all relations R. So we say a relation R in a set A is an equivalence relation if it's reflexive, symmetric, and transitive. And we say that two elements A and B are equivalent if they are related by an equivalence relation R. Okay. So let's take a look at example number 1. This reads, let R be the relation on the set of integers such that A comma B is in R if and only if A equals B or A is equal to negative B. Show that R is an equivalence relation. So we have to show 3 things. We have to show that it is reflexive. So to determine whether or not it's reflexive, remember it needs to, for every element of the domain, so in this case for every element A and A, there needs to be the element A comma A in B, in R, in the relation R. So this is a question. For every element in the domain, is A comma A in the relation? Well, let's see. A equals itself. So that means that A comma A will be part of the relation. So it is reflexive. Now, is the relation symmetric? Well, let's see. What happens if A comma B is in R? If A comma B is in R, then two possibilities. We have two possibilities. Then either A is equal to B or A is equal to negative B. Okay, if A is equal to B, then that means that B is equal to A. And in such a case, it means that B comma A is part of the relation. If A is equal to negative B, that means that B is also equal to negative A. So that means that B comma A is also going to be part of the relation. So in either one of those cases, if A comma B is part of R, then B comma A is also part of R. So that means that it is symmetric. Okay. And the last property is transitive. Is it transitive? Well, let's see. Again, we're going to take some arbitrary elements. let's just take A comma B in R and B comma C in R. So what happens if this is the case? Then four possibilities can occur. We have four different possibilities. The first one is that A is equal to B and B is equal to C, in which case we're going to get that A is equal to C, and that means that A comma C will be part of R. Okay, the second possibility is that A is equal to B and B is equal to negative C, in which case we're going to get that A is equal to negative C. And that is also, that means that A comma C will also be part of the relation. The next possibility is that A is equal to negative B and B is equal to C, in which case we're going to get that A is equal to negative C. And again, that means that A comma C is part of R. The last possibility is that A is equal to negative B and B is equal to negative C, in which case we get that A is equal to C. And that means that A comma C is also part of R. So in any one of those possibilities, if A comma B is part of R and B comma C is part of R, that means that A comma C will be part of R. And so the answer here is yes. So because it is all three, reflexive, symmetric, and transitive, that means that R is an equivalence relation. All right, let's take a look at example number 2. For example number 2, we have let R be a relation on the set of real numbers such that A comma B is in R if and only if A minus B is an integer. Is R an equivalence relation? Well, let's start with reflexive. If we want to check if for every integer A that is a real number, for every element A that is a real number, is it true that A comma A will be part of the relation? Well, A comma A will be part of the relation, and the reason why is because A minus A is equal to 0, and 0 is an integer. And so that means that it is reflexive. The next one is symmetric. So we're going to check whether or not it's symmetric. Now, for any two real numbers, is it true that if A comma B is in the relation, then B comma A is part of the relation? Well, let's see. If A comma B is part of the relation, then that means that A minus B is equal to K, where K is some integer. Now, if we multiply both sides of the equation by a -1, that means that we're going to get B minus A is equal to negative K, right? So negative K is also an integer, which means that B comma A is also part of the relation. And that means that it will be symmetric. Okay, the next and last property is it transitive? Well, let's take again any three real numbers, A, B, and C. If A comma B is in the relation and B comma C is in the relation as well, then that means that there have to exist two integers. So let's just call them K and Q, such that A minus B is equal to K and B minus C is equal to Q. Now, if we take the sum of these two numbers, a minus b, with b minus c, we're going to get that a minus c is equal to k plus q. And so because k is an integer and q is an integer, that means that k plus q is also an integer. And the result of that is that a comma c is also part of the relation. And so because that is the case, that means that this relation is transitive. So again, because all three are satisfied, that means that R is an equivalence relation. The next example I'm not going to complete because I am going to let you work on this during your lab time. But example number 4 reads, let R be the relation on the set of real numbers such that x comma y is part of the relation if and only if x and y are real numbers that differ by less than 1. That is, and there is a typo here, that is the absolute value of x minus y is strictly less than 1. That equals symbol should not be part of the inequality. Show that R is not an equivalence relation. So if it's not an equivalence relation, that means that there is one of those three properties that it fails, so either reflexive, symmetrical, or transitive. So we're going to figure out which one of those three it is. Is it reflexive? Well, let's see. For any real number, let's call it A. For any real number in R, A comma A is going to be part of R because absolute value of A minus A is equal to absolute value of 0, which is 0, and that is less than 1. So it is reflexive. That's not the property that fails. Is it symmetric? Well, let's say for any two real numbers, if A comma B is part of R, that means that A minus B has to be less than 1. And if that is the case, then we can factor out a negative 1 from the A minus B, and we'll have absolute value of negative B minus A is less than 1. And then we can separate that into absolute value of negative 1 times absolute value of B minus A will be less than 1. And absolute value of negative 1 is simply 1. So we get a 1 times B minus A, or absolute value of B minus A is less than 1. So the final result would be that absolute value of B minus A is less than 1. So because this is the case, that means that B comma A will be part of the relation whenever A comma B is part of the relation. The next property to check is transitive. Is it transitive? Well, again, see for any three real numbers, A, B, and C, if A comma B is part of the relation and B comma C is part of the relation, that means that absolute value of A minus B is less than 1 and absolute value of B minus C is less than 1. Okay. What that means, if we write or if we consider the definition of absolute value, that means that negative 1 is less than A minus B, which is less than 1, and B minus C will be greater than negative 1 but less than 1. Okay, so what we can do now is we can combine these two inequalities to come up with the result that, well, if A minus B has to be greater than negative 1, and I add A minus B to all three parts of this inequality, the result in the middle is going to be greater than negative 2. So we're going to get something like -2 is less than a minus c, because that is the result of adding a minus b plus b minus c, right? The negative b and the b will cancel, and we'll get an a minus c. And that's going to be less than, well, again, if a minus b has to be less than 1 and b minus c has to be less than 1, then the sum of the two has to be less than 2. Okay, now using again the definition of inequality, that means that the absolute value of a minus c is going to be less than 2. And so we see then that the relation fails to be transitive, right? So that means that a comma c is potentially not in R. So that means that R is not transitive. And so that means that R is not an equivalence relation. Okay, we're going to take a look at one more example which asks us to determine whether R is an equivalence relation. In this case, they're saying let n be a positive integer and s be a set of strings. Suppose that Rn is a relation on S such that S and T will be part of the relation if and only if S is equal to T, or both S and T have at least n characters and the first n characters of S and T are the same. Show that for every set S of strings and every positive integer n, Rn is an equivalence relation on S. So this is actually very similar to what we saw in the introduction with the variable names in the C language. But in this case, we're just kind of generalizing that idea to be for any set S of strings and any number of characters n. Okay, okay, so again, we have to go through the 3 properties of an equivalence relation, which is reflexive, symmetric, and transitive. Okay, so is it reflexive? Well, for any string, let's call it S. For any string S in the set of all strings, S comma S is going to be part of Rn because, well, it's a copy of itself and it's going to contain exactly the same characters, including the first n characters. And because S shares the same first n characters with itself. Okay, is it symmetric? Well, let's see. Let's consider any 2 integers. So, any 2 strings. So let's say for any strings S and T and S, S comma T being in Rn means that S has to have, let's call them character 1, character 2 down to character n, and maybe the rest Sn plus 1 down to S capital N, where capital N is the length of string S, and T will have the same first n characters, so C1, C2 down to Cn, and then Tn plus 1 down to Tm, where again m is the length of string T, so I'll just write m is the length of T, n is the length of S. Okay, But what matters here is that the first n characters are shared in common. And that's what it means for s comma t to be part of the relation. So if that is the case, then it's also true that t comma s is going to be part of Rn for exactly the same reason. Yeah, so it is symmetric. Is it transitive? Again, we're going to now take three strings. So let's just say S, T, and R that are part of the set, of strings. If S comma T is part of the relation and T comma R is part of the relation, then what does that mean? Well, if S comma T is part of the relation, then we're going to have something like this, right? We're going to have that S has characters C1, C2, down through Cn that are shared in common with T. We also have a string R that because we have the ordered pair T comma R as part of the relation, that means that the first n characters of T have to, of R have to be the same as those of T. So it is going to have C1, C2, down through Cn, and then Rn plus 1, and maybe down to Rq, where Q is the length of R. So again, these two we have because ST is an RN, and then these two we have because TR is an RN. And so now we see that because the first n characters are shared in common between S and R, that means that S comma R also needs to be part of the relation. So Rn is transitive. And now, since it satisfies all three properties of an equivalence relation, we can conclude that Rn is an equivalence relation. All right, so this brings us to equivalence classes. We're going to let R be an equivalence relation on a set A, so that means that A is the domain. The set of all elements that are related to an element A of A is called the equivalence class of A. And so the equivalence class of A with respect to R is denoted by this A inside brackets with a subscript of R. So in particular, we just write that the equivalence class of A is the set of all elements S such that A comma S is an ordered pair in R. And again, something that perhaps would be helpful to remember here is that S is an element of the domain. Okay, so we could be a little bit more explicit and write the set in this form. When only one relation is under consideration, then we can delete the subscript and simply write A between brackets for the equivalence class. Okay. Now, one thing that is important to note is that if we're looking at the equivalence class of A and we pick out some element, let's call it B, then B is called the representative of the equivalence class. But because all of the elements that are part of the set are equivalent to each other, it doesn't matter what we choose as a representative of the class. There's nothing special about that particular element that's chosen as a representative. They are all equivalent under R. Okay, so let's take a look at example 6 to get a better idea of how this works. What is the equivalence class of an integer for the equivalence relation that is described in example 1? And if we go back to example 1, the equivalence relation was the one that consisted of ordered pairs A comma B, where A either equals B or A equals negative B. Okay, well, if we think about, again, let's write the definition. The equivalence class of a set of an element A, that is going to be the set of all elements B that are part of the domain, and in this case the domain was a set of integers. R was a relation on the set of integers, so it's the set of all integers such that that integer could potentially be paired up with A under relation R. Now, how can it be paired up with A under relation R? It can be paired up if A is equal to B or if A is equal to negative B. That's in general the equivalence class. Now we can simplify that expression, because if we think about it, that means that for any element A, it can only be paired with itself or with negative of itself. So that means that this is the same as the set containing two elements, A itself or negative of A. Right? It can only be paired with itself or negative of itself. So for instance, if we have the equivalence class of R, the equivalence class of 1 with respect to R, 1 would only be able to be paired with itself, or which is 1, or with negative itself, which is negative 1. If we think about the equivalence class of negative 3 with respect to that relation, negative 3 can only be paired with negative 3, which is itself, or with negative of that, which would be positive 3. So the equivalence classes will contain only two elements, the element itself and negative. Example 7 is asking, what is the equivalence class of the string 0, 1, 1, 1 with respect to the equivalence relation R3 in example 5 on the set of all bit strings? Okay, so again, let me just write down in general what the equivalence class is going to be. So S is taken from the domain of the set of all strings. Okay. So it's going to be the set of all strings, which I'm going to call T, that are part of S, such that they share the first three characters. Okay, so such that S is equal to character 1, character 2, character 3, and then the fourth character can be different. And T is equal to character 1, character 2, character 3. The fourth one can be different all the way to the last character. Okay, so they share the first same three characters. So that means that if we're trying to find the equivalence class of 0, 1, 1, 1 with respect to R3, then that would be the set of all bit strings, right, or the set of all strings, but in this case, they say the domain is all bit strings. So it's going to be all bit strings, I'll call them B, and I'll call capital B the set of all bit strings. Such that B is the string consisting of 0, 1, 1, and then some other 4th bit, 5-bit, all the way to, I don't know, let's just call it a capital N bit. Or if we want to write it out in words, all bit strings beginning with 0, 1, 1. We now take a look at the following theorem, which reads, let R be an equivalence relation on the set A. So set A is a domain. These statements for elements A and B in A are equivalent. So the first statement is that A comma B is part of the relation. Then the second statement is that the equivalence class of A is the same as the equivalence class of B. Meaning the two sets are the same, because remember, this is a set and this is a set, so they contain the same elements. And then the last one, there is a typo, so there is a union between the two equivalence classes. There should be an intersection. So it reads, the equivalence class of A intersect the equivalence class of B is non-empty, meaning the sets A and B, equivalence class of A and B, are not disjoint. And so we are going to prove this theorem. In order to prove statements of this type, where we have to prove that these three are equivalent, we start by assuming that the first statement is true and that the second statement is going to follow from the truth statement of 1. So in other words, we have to prove that I implies, or 1 implies 2. And that means that we'll treat as a given the fact that A comma B is part of the relation, and then the goal is going to be that showing that the equivalence class of A is equal to the equivalence class of B. Now, because the two are sets, in order to show that two sets are equal, we need to show that the equivalence class of A is a subset of B and vice versa. Okay, so we're going to assume A comma B is in R. We must show the following. Equivalent class of A is a subset of equivalence class of B. And 2, the equivalence class of B is a subset of the equivalence class of A. So we're going to be showing 1, and I guess I should label these differently because these are already labeled the same. So I'll call this 1 and this numeric 2. Alright, so to show that 1 is true, pick an arbitrary element that is part of the equivalence class of A. So pick C that is part of the set. And remember, whenever we show subset, we want to show that if it's part of the smaller set, then it has to be part of the larger set as well, that is encompassing the smaller set. So we're going to pick an arbitrary element C and A. And then what does that mean? Well, if it's part of the equivalence class, then by definition, A comma C has to be part of the relation. Okay. Now, since A comma B is part of the relation, and R is transitive by definition, well then that means that B comma A has to be part of the relation. Okay, so notice what we have so far. We have that A comma C is part of the relation because C is part of the equivalence class. Then we have B comma A is part of the relation because R is transitive. If we take these two together, Again, because R is transitive, B is in A, B, A is in R, AC is in R, must mean that BC is in R. Okay, so again, since R is transitive, B comes C will be in R. Now if BC is in R, that means that C needs to be part of the equivalence class of B. So hence, C is part of the equivalence class of B because, well, the equivalence class of B contains all of the elements that are paired with B, and C is one of them. So C has to be part of the equivalence class. Since C is was chosen arbitrarily, there was nothing special about C. The result is going to hold for all elements C that are part of the domain. Meaning, if C is part of the equivalence class of A, then C is going to be part of the equivalence class of B. And that is definition of subset. And so we've proven this first part. The second part is proven exactly the same way, except that now we pick an arbitrary element C and B, and then show that that element will also be part of A. Okay, so I'll just say here, 2 is proven using the same argument. Or I should say similar argument. You just need to switch around the variables. So we're going to skip proving 2 because it's nearly identical to 1 and move on to the next statement that needs to be proven, and that is we've already shown that 1 implies 2, meaning this implies this. We're now going to show that 2 implies 3. Okay, so now 2 implies 3. Okay, in order to show that, we assume that 1 is given, that 2 is given, so that means that the equivalence classes are the same. And our goal becomes to show that the intersection of the two classes is non-empty. Alright, so to prove that, we're going to pick an arbitrary element. Let's call it C in the equivalence class of A. Then, since A and B are the same sets, that means that C also has to be in the equivalence class of B. And, well, what does that mean? Well, that means that the intersection of the two sets cannot be empty, because C is in the intersection. So since that is the case, it follows that A intersect B is non-empty. The last statement that we need to prove is that statement 3 implies statement 1. That means that given that the intersection of the two equivalence classes is not empty, then A comma B has to be part of the relation. And so what we're going to do is we're going to pick some element in the intersection, which we know has to exist because it is non-empty. So I'll just say since equivalence class of A intersect equivalence class of B is non-empty, then there exists some element C in the intersection. And then we'll say for such element, it is the case that C will be part of the equivalence class of A, and C will be part of the equivalence class of B. And that means that A comma C exists as an ordered pair in the relation R, and B comma C exists as an ordered pair in relation R. Also, since R is transitive, since R is symmetric, it means that C comma B is going to be part of R. And then since R is transitive, A comma C is in R, C comma B is in R. So that means that A comma B has to be in R. And that is the goal, so we've made it through. Alright, so now that we've shown that 1 implies 2, and 2 implies 3, and 3 implies 1, we can conclude that all 3 statements are equivalent, and that is because now if we wanted to prove that 3 implies 2, then we could go through 1, and then from 1 to 2 to have the implication 3 implies 2. And so here we have 2 implies 3, and then 3 implies 2 makes the statements equivalent. Okay, so this technique of proof finally proves the whole theorem.